Welcome to the video series of System Programming and Compiler Construction. We have already started with the fifth module, that is Compilers Analysis phase. Let's continue with that. In this video, I will be covering the following topics, that is specification and recognition of lexemes, design of lexical analyzer generator, syntax analysis, and parsing techniques. Before we jump into understanding how a lexeme is specified and how a lexeme is recognized, let us briefly revise what was done in the previous lecture. So in the previous lecture, I had specifically given you all the distinguishing points, or as I had explained you how a lexeme is different from token, how a token is different from a pattern, and how a pattern is different from a regular expression. So we'll just quickly revise whatever was done in the previous lecture. So we know that it is the lexical analyzer who is responsible for identifying various lexemes. And these lexemes are then converted into tokens. These lexemes are then converted into tokens by my lexical analyzer. But the question is, how any lexical analyzer will be understanding whether a specific group of character can be considered as a lexeme or not. So, in other words, we need to make our lexical analyzer knowledgeable. We need to provide our lexical analyzer some kind of knowledge using which the lexical analyzer will easily identify various types of lexeme. And this knowledge we are providing to lexical analyzer in the form of patterns. That is, based on some predefined patterns, the lexical analyzer will be able to distinguish the type of lexeme. And how are these patterns written? So these patterns are written using regular expressions. So it is the regular expression which helps us to define various patterns. Using these patterns, the lexical analyzer will be identifying lexeme, and then these lexemes will be converted into tokens by my lexical analyzer. So let us understand how these regular expressions are written. As I said, for specifying lexeme pattern, regular expressions are used. While regular expression cannot express all possible patterns, but they will be effectively helping us in specifying those patterns which we need for tokens. So the various types of tokens or lexemes in broader sense are identifiers, keywords, operators, punctuation, and literal. The words which are considered as keywords can also fall under the category of identifier, provided they were not a reserved word. For example, int can be considered as an identifier, but we are not considering it as an identifier because it is said to be a reserved word by C language. Hence, hence the statement is that it is not possible to express all patterns. So whenever we are trying to write a lexeme or a program, a lex program, we try to write the regular expression in such a way that will help any lexical analyzer to identify the tokens. Let us understand what are the various regular expressions. So assuming that sigma, that is my input alphabet, is either A or B, the first way of writing a regular expression is A. This standing line is representing the OR operator, and then there is B. So if I have this kind of regular expression, the valid strings will be A or B. If I'm writing this kind of regular expression, then the valid string will be AA, AB, BA, and BB. A star. Star is nothing but whenever you are writing star in your regular expression, means it says that zero or more occurrence of that particular expression. Because it is A star, means it will be having zero or more occurrence of A. Thus, my valid string will have epsilon. Epsilon because there is null string. Okay. Epsilon, A, AA, triple A, 4 times A, and so on. And lastly, it is A or B star. If you remember, the same thing was written in TCS as A plus b the whole star. So this we were writing in TCS. But when we are writing a Lex program, we should not be using the plus operator. Hence this plus operator is replaced by a standing line, which is my OR operator. So these are the possible valid strings for the expression A or B star. Thus, it is the regular expression which is helping us to write patterns. These patterns are used by lexical analyzer to identify lexemes, thus converting the identified lexemes into tokens. Let us look at more of the regular expressions which can be written for identifying tokens. So suppose if I want my lexical analyzer to identify numbers, then I will be writing my regular expression as 0-9. This says that any single digit number or any input which is a single digit can be considered as a number. Further, digits giving me digit plus. Plus means one or more occurrence of the given expression. So here I can have my input as 12 because 1 and 2 falls in the category of digit, and because of plus sign I should have at least one occurrence of that particular range of numbers. Then in my broader sense, if I want my lexical analyzer to identify numbers which are integer, floating point or exponential number, then this is how my regular expression is written. Here the question mark means at least one, that means a single occurrence. Okay, so it is single occurrence of the pattern which is mentioned. If I want to identify a character, then this is how we write a regular expression in our Lex program. If I want to identify an identifier, then this is the regular expression which is mentioned. So it is, we know that an identifier should always start with a letter. Hence, the expression starts with a letter followed by one or more occurrence of either letter or digit. So this is how my identifier is defined. Then for if, as I said, if can fall into the category of identifier, but it doesn't fall because it is considered to be a reserved word by some of the programming languages. Hence, keywords like if, else, then, return, so on and so forth are provided into double quotes whenever we are writing our Lex program. So how are we basically writing it? So if you want to write regular expression for keywords, it will be double quotes if, close your double quotes, or double quotes else, close your double quotes, or double quotes return, close your double quotes. So this is how you can write your regular expression for keywords. Then for relational operator, if you observe, each relational operator is specified separated by an OR operator. Rel op is the short form of relational operator. Last is white spaces. Any blank tab or new line is considered as a white space. Now, transition diagram. I just now said that the lexical analyzer is responsible for identifying lexemes based on some pattern. This we have already done in TCS, that is theoretical computer science, that whenever any pattern is written or whenever any regular expression is written, this regular expression can always be converted into epsilon NFA, and this epsilon NFA is converted into DFA. So for any regular expression, it is possible to create epsilon NFA, and the epsilon NFA can be reduced to DFA. Likely, or you can say in the this is the logic used by the lexical analyzer. Lexical analyzer is also made knowledgeable with the help of regular expression. So I have a lexical analyzer who is made knowledgeable with the help of regular expression. This lexical analyzer is responsible for converting the regular expression into DFA, or you can also call it as a transition diagram. And once the DFA is constructed for every regular expression written inside or written in the program, whatever input comes to lexical analyzer, this input is scanned on this DFA. And if this DFA reaches the final state, then only the string will be accepted. Otherwise, the string will be rejected, or the string will be considered as a valid lexeme. Otherwise, it will not be considered as a lexeme. Thus, as the slide says, as an intermediate step in the construction of lexical analyzer, the patterns are first converted into flowcharts, which are called as transition diagram, or you can also call it as a DFA. Thus, regular expression patterns are converted into transition diagram. Let us understand how a transition diagram is created for any relational operator. So we start with the start state. Now, if in the start state I receive a less than sign, then I go to my next state. Now, the possible input after less than sign can be equal to, it can be greater than sign, or it can be anything else. It can be a space also. So to decide whether less than sign is a lexeme or there is something else to be added to the existing less than sign to make it as a valid lexeme, we need to look ahead one more character. And this concept of looking ahead one more character was explained by me when I was explaining input buffering. If you want to understand that concept, you can please go through the previous videos of mine. So, assuming after less than sign, there is an equal to operator read. Now this becomes a valid lexeme. Thus, I will make that equal to reach the final state, stating that the regular expression or the relational operator that is received is a less than sign. Thus, it is a valid lexeme. But if after less than sign a greater than sign is encountered, again I will make it reach my final state, stating that the relational operator encountered is NE, which is not equal to. And after less than sign, if I am encountering any other character, I still say I will be reaching my final state, but now the relational operator identified is my less than sign. But if in the starting state, instead of less than sign, I'm getting an equal to operator, then I again reach my final state, stating that the relational operator encountered is an equal to sign. The aim of this slide is to make you understand that for every regular expression, the lexical analyzer is responsible for generating a DFA, and the input string is parsed on this DFA to decide whether the string that is entered is a valid lexeme or it is not a valid lexeme. I hope it is understood. With that, I continue with my next slide. So this is the entire this is the entire transition diagram for relational operator, and this diagram is taken from the reference book Ullmann. To make it more clear, let us understand how a transition diagram is created for an identifier. So this was the regular expression which was put up in the previous slide, and I had explained why the regular expression is written in this way. So digit has the expression 0 to 9 and letter had the expression A to Z capital, A to Z small. We start with the initial state, that is 0. If I encounter a letter, I will go to the next state. If I encounter a letter or a digit, I remain in the same state. Then I look one more character ahead, and based on that character, I will reach my final state, stating that the input string is an identifier. Because it is an identifier, this information, that is token name and ID, token ID, will be saved into the symbol table. Very important slide from examination point of view. How is a lexical analyzer generator designed, or what is the design of lexical analyzer generator? Let us understand the slide. As I said, a lex program is turned into transition table and actions which are used by finite automata simulator. So we know that it is the Lex program which has some regular expressions written into it. These regular expressions are converted into transition diagram or DFA to check whether the given input string is a valid lexeme or not. But when we talk about a program, now this is not explained by me in any of the slide, but I'll put it over here. When you talk about any Lex program, when I write my Lex program, the program will be having, or the program that is created with .l file as extension. This .l file is then given to a Lex compiler. Okay, this .l file is given to a Lex compiler. This Lex compiler is responsible for producing a C file, that is lex.yy.c. It is this C file where our transition diagram is defined. Defining a diagram in a C program is difficult, hence the diagrammatic structure is replaced by transition table and actions. Okay, so this is the lex.yy.c file which has transition table and actions. This table and the actions mentioned will help the lexical analyzer to decide whether a entered input is a valid lexeme or not. So Lex program which has regular expressions is given to the Lex compiler. This Lex compiler is responsible for generating transition diagram or table. This transition diagrams or this transition table and actions are used by finite automata simulator. It is this simulator who is responsible for reading input from the buffer. So if you now understand the concept, the automata simulator which is over here reads every character from this buffer. This character is then passed on this transition table. Based on the actions mentioned, the lexical analyzer can decide whether the entered input is a lexeme or not. Continuing with the same. Following are the components that are created from the Lex program by the Lex itself. So the Lex itself is responsible for creating something. As I said, the first is, I'll take another pen. Okay, so the first is my transition table. So the Lex compiler itself is creating the transition table for the program that is written. There are some functions which are not being compiled by the Lex compiler. These functions are transferred as it is to the C program. Say for example, if I have written a Lex program which has some C statements into it, then those C statements are not compiled by the Lex compiler. Instead, they are passed as it is to the C file which I just said, that is lex.yy.c. The actions from the input program. So if you, I'll take one more video, I'll put another video where I will be explaining you how to write a Lex program, how to execute it, and how to view the output. So in the Lex program, I mentioned the actions to be taken when a valid lexeme is encountered. These are invoked by the simulator as and when it is reading the input. To construct the automata, take each regular expression pattern in the Lex program and convert it into NFA. As I said, we need a single automaton that will recognize lexemes matching any of the patterns in the program. In other words, what the slide is saying, that if I have written 10 regular expressions for my lexical analyzer, you cannot have 10 different transition table and 10 different actions. What we do is we combine all these patterns into one transition table. In other words, multiple NFAs are combined into a single NFA. This is an example of the same. So the first NFA is for matching pattern A. The second NFA is for matching strings ending with ABB or matching ABB. And the last is for matching a regular expression A star B plus. This way, multiple NFAs are combined into single NFA and the input is parsed on these NFA. If we reach any of the final state, the string is considered to be a valid lexeme, otherwise it is an invalid lexeme. This was all about lexical analysis in detail. As we know, we are doing the fifth module, that is analysis phase of the compiler. The second step under the phases of compiler is syntax analysis. In the previous videos, we have understood lexical analysis in detail. From this video, we will start understanding syntax analyzer. How syntax analyzer is responsible for creating parse tree. For creating parse tree, there are multiple parsers which we need to understand. In the syllabus prescribed by Mumbai University, for top-down parser, we are going to study LL1 parser only. Under bottom-up parser, there is bottom-up parser ideally is known as shift-reduce parser. So I will be taking numerical on shift-reduce parser. Under bottom-up parser, there is operator precedence parser, which I will be covering in the next lecture, and there is SLR parser. So this is one more parser under which numerical will be taken by me. It is the syntax analyzer. It is the syntax analyzer who is responsible for accepting token from the lexical analyzer. So syntax analyzer tells the lexical analyzer to give token. It is then only the lexical analyzer will transfer token to syntax analyzer. As soon as the syntax analyzer or the parser receives tokens from lexical analyzer, it will verify these tokens on the grammar which it already has. If the token is verified by the grammar, then the parse tree is generated. In other words, the parser is responsible for constructing parse tree for programs which are well formed. And this parse tree is then given to the next step, that is semantic analyzer. These two steps are responsible for using the symbol table. The parse tree thus formed by matching the string with a predefined grammar is then sent to the next step. But if the input string doesn't validate with the grammar that is available with syntax analyzer, then the parsing action will stop and an error is reported to the user. Importance of syntax analysis. Syntax analysis is used to check if the code is grammatically correct or not. And this is checked based on the grammar rules which are provided with the syntax analyzer. Just to throw a light on this, like lexical analyzer is made knowledgeable with the help of patterns, syntax analyzers are made knowledgeable with the help of grammar. Based on the grammar which a syntax analyzer has, it will validate the input on that grammar. If the input gets validated on the grammar, then the parse tree is created. Otherwise, as the second point says, an error will be detected and will be reported. Syntax analyzer rejects invalid code before actual compilation. It also helps us to make sure that every opening bracket has its corresponding closing bracket. Each declaration should have a type and that data type must be existing. Definition of parse tree. Parse tree is a graphical representation of the derivation. It is used to show how the given string is derived from the starting symbol. The start symbol is said to be the root of the parse tree, or the start symbol always becomes the root of the parse tree, whereas the remaining characters, that is the terminals, that is the small characters, will become the leaves of the parse tree. What are the various parsing techniques that are used for creating a parse tree? So there are two parsing techniques, top down and bottom up. Top-down parsing is responsible for creating parse tree from root to leaves, whereas bottom-up parser is responsible for creating parse tree from leaves to root. Examples of top-down parser are recursive descent parser, LL1 parser. LL1 parser is also known as predictive parser. There are multiple bottom-up parsers. Some of the examples on the slide are LR parser, SLR parser, CLR parser. Let us briefly understand what are the types of parser. So parsers are of two types, top-down and bottom-up. Top-down is further categorized with top-down full tracking, full backtracking, and top-down parser without backtracking. Under top-down parser without backtracking, we have two types, recursive descent and non-recursive descent, that is LL1 parser. Recursive descent parser is also known as backtracking parser or brute force parser, whereas non-recursive descent parser is also known as predictive parser or LL1 parser. Under bottom-up parser, we have operator precedence parser and LR parser. LR parser is further categorized into LR0, SLR1, CLR1 and LALR1 parser. In my next video, I will be starting with operator precedence parser and we will be looking on to the numericals on operator precedence parser. Thank you for your patience listening. So as I said, in my next lecture, we will be understanding bottom-up parsing in detail, what is all about bottom-up parsing, why operator precedence parser, what is operator precedence parser, and numericals on operator precedence parser. So stay tuned for the next video, which is very important from examination point of view. I will be taking numerical on operator precedence parser. Thank you everyone for your patience listening.